Ready?
Yep.
Okay. I'm Raul from Antenna World in Miami, Florida. And I've been playing with antennas since I was 16 years old. Started in ham radio when I was 15. And kind of the hobby.
Make sure you're checking Twitter if you get updates on when the box has been found. Any hits,
The hobby. I'll wait for him. The hobby became a business. And it's been fun. And still enjoying it. And it's not just for profit, it's for fun. So anyway, I had to pick a quick, something to help you guys out when choosing an antenna. Because I go a lot around eBay. We have some stores on eBay where we get rid of older antennas and stuff like that. So I see a lot of false information, a lot of claims going on with what they're offering the general public. And basically, I thought this was, because every time I go on the internet and look around, I'm like, oh my God, look at this. How can I compete against this when I'm saying the truth? They're having all these claims, So basically, I just called it choosing your next antenna, types, power, sizes, and the truth. And obviously, we just got a short time, so can't get too deep into anything. And I'll start with, first of all, just feel free to ask a question, because if we wait till the end, you forgot what the question was, and we're far away from that part of the information. So I'll just start with, I made a notes here. What's dB gain? You hear this all the time. This is decibels of gain, and this is the wanted power where you want it, at the horizon. And antennas don't create power, they manage it. Very simply, a simple dipole puts out a globe of signal, and as soon as we start adding elements and start managing this, we start getting rid of the wasted signal up and down and send it where we want it, all around. So, and that's measured in decibels, dB, units of 10, started by Mr. Alexander Graham Bell in 1870-something. And it's a logarithmic scale. So 3 dB doubles your power. And if you lose 3 dB, you lost half your power. So part of this is, showing you guys when you see some antenna that's 3 feet tall and it's on 2.4 gigahertz, that's about a 9 dBi antenna. And then you see one next to it saying they have 12 dBi, that's double the power. Well, if everything's true, that antenna has to be 6 feet tall, okay, to get to 12 dBi, as an example. And that's the first step where somebody's lying to you. And so I wanted to touch on that. And this happens with antennas, directional antennas, log periodics, dipoles, everything. And as a basic thing, I wanted to say, the wavelength, I'll show you about the wavelength later. And now, remember we said about managing the power. So we've got an omnidirectional radiating all around, and we're wasting all this here and all this here. So when we increase the gain to 3 dB, we just doubled the power on the horizon. We go up another 3, we doubled it again on the horizon. So what happens then is that it starts getting very narrow. And when you get to about 10 or 12 dB, you've got a elevation of around 10 degrees all around. So that omnidirectional stick has to be vertical, otherwise you're radiating into the ground and at the moon, or vice versa. And basically we also call omnidirectional antennas equally poor in every direction, because you're doing 360, and the customer wants 360, and they want all this gain, and what's really happening is we're thinning it out more and more to give you the 360. So for I mean, you see on cell towers, they're called sectorials, and we even have sectorials where I work. And they're big old panels. And what they're doing is they're stacking a bunch of panel antennas in there to create this wide but high gain. And those are sectorials, and you'll see 180-degree sectorials. So from here to here, you've got fantastic 15 dB gain and nothing behind you. There's no waste. So a lot of them are 120 degrees, and then they put 3 on a tower to cover 360 degrees. And that's really good stuff. It's a little bit wider, and it's what's on those cell towers. And let me see if I can show you some of this. And on a directional antenna, you either go long and narrow, or you're going short and wide. And sometimes we ship an antenna to a customer who was using a 6 or 7 dBi black stick. You know, he's got this monster antenna now, and he says, now I see 4 access points. I used to see 15. And it's because he had 15 close by. Now we're pointing right over there. We're seeing the 3 that are in that vector. And he's ignoring everything that's here. So that black little stick was doing better for all this here, everything around me. And now we've got this terrific beam in this direction. We won't even see this. The signal to the left and to the right quickly drops to like minus 5, minus 10. And that stick might have been 4 dB. So you can see what's going on with that. And that's part of you know, the retailing to the Wi-Fi crowd and the cellular crowd and all that. Let me see if I can show you some of this here. Okay, that's an omnidirectional pattern. See, that's looking up from the sky. And it's very simple. It's just all around. If I can get that here. And here is an example of a, on the left, there's like a 35-degree pattern that's 14 dBi, and on the right, this is the grid, 24 dBi grid. So that tip should be around 23 to 25 dBi, and very narrow. And if you look here, you'll see just to the left and to the right how weak that signal is. While the little stick, the cheap little stick, was going to do all this. So let's just give you an example of what's going on there. And oh, here's a pattern for an Omni. This is an Omni that.
Wait a second. I mean,
that's it. Go ahead.
Back a bit. With the cheap little stick, did that go out as far as that single beam?
Oh no.
Okay.
The little stick is way in here.
Okay, gotcha.
Way
That's what
in here. Yeah.
Okay.
Yeah, that's why the guy here isn't going to see.
Yeah.
You know, so now he has to lean around. And any questions yet? Yeah. If the Omni is up high, it's radiating. I'll show you. It's radiating all around. Let me see if I can get to it. Well, here's an example of this directional that's here. So you see this is a 31 degree, 14.5 dBi, typical stuff. Okay, this is getting into the truth about antennas, and I guess I'll get into that now. Omni patterns, about directional antennas. So we went through the directivity. Any questions about directivity? This is what it's called. What's the small 3 degrees. You know the satellite antennas for VSX, DirecTV? Those things are like 3 degrees wide. And there's a point at which you can go bigger and bigger and bigger on a dish, on a parabolic dish, and you just don't get under 2 or 3 degrees. The signal just gets stronger. And I don't have the mathematical formula for that, but I've seen it. And that's why you just moved that dish and you lost the satellite TV. And now here, near field, far field, okay. Now, quarter waves and half waves. Okay, notice here, first I'll say, a quarter wave at 850 megahertz is cellular frequency. I know this by heart, but I wrote it just in case. It's 3 inches, 3.3. At 2.4 gig, a quarter wave is 1.17 inch. Like this. At 5 gig, it's a half inch. Okay, that's a quarter wave antenna. So what happens is the capture area of a half inch of metal is very little. So, you know, it's all the wave is going to just pass over. So you'll always see a gain antenna like this. This is probably a 2.4. I found this on the web. I had to run out to catch the airplane, and I couldn't get all my files out. So then in the hotel last night, I picked up some of this stuff. And for this to be a truthful antenna, and this looks fairly truthful on 2.4 gigahertz, you've got here about a half a wave, and then you have a tuning network here, and then here you have about a 5/8 wave and another 5/8 wave here. And I'll show you antennas that are, I can just look at stuff like this and know when they're totally correct. And I'll show you a pattern, a signal pattern, what's going on. So this is a 2.4 gig. This is what's typically inside those black sticks, unless we printed a circuit. Sometimes we'll print it, and I'll show you a printed circuit. Especially if we're making it in Florida, this is too much labor. You know, you can do that at $2 a day, but not at $15 an hour. So, okay, there's a printed one. See? And we make stuff like this on 2.4. So here, and as an example, that's either a quarter wave or a half wave. Quarter wave or a half wave. That's a half wave because you got a quarter wave right here. So this is a 2.4 gigahertz printed antenna. And in fact, you guys can do this at home with how we started design. I'm going to get into that, but we use copper tape. Where you go to Home Depot and you buy aluminum tape, and you can do this. Okay? You can also do practice on any frequency you want with copper tape and aluminum tape, especially copper tape because you can solder to it. It's a lot of fun. It just takes a little time. And so this is the truth. And here is, I have to sell this. I mean, I sold this. It's got my logo on it because some customer wanted something for $2 and we had to ship 5,000 for $2. So that is a crap antenna. This is really crap. Okay, so, you know, something like this, for example, I think it was supposed to be on 1.9 gigahertz. And there's just no way there's any resonance up here. That's as good as having a coat hanger. So instead of this radiation pattern doing this, it's doing this and doing this, and it's crap. And this is what the market is flooded with stuff like this because nobody can measure it. It costs a lot of money to measure this. And the Chinese who make this, they tune to SWR. Anybody know what SWR is? Right. The resonance. And radio is one of the first things we know. So you can buy an SWR meter for $100 or $500 for the fancy one. But the test chamber in China, they can't afford it to go to the university or the government building every once a year. So they got to get the order out. So they get on the meter and they tune it. We got 1.5 SWR, and they ship it. And we sell some antennas to Colombia or Venezuela where we call it a 7 dB, and they insist on calling it a 10 dB because I showed them the pattern of this. It's -3. Okay, so that means they fed a watt into it. They lost half a watt on the cable, and they lost another half a watt on the radiation, which was not here. It was probably up here. That's the kind of fun stuff that. So here, there's no way that you have space for a quarter wave here. And then here, this is totally wacko. You know, it just doesn't make sense. When you see an antenna like that, and if you know, for example, that a quarter wave at 850 is 3 inches, and a quarter wave at 2.4 gigahertz is 1 inch and a quarter, say 1 inch and a quarter or 1.2, you know that's impossible. For that antenna to be truthful, let's say it's 2.4, it should have, this was a little lower, that's a little smaller, and that cuts off maybe right there. And you have a 5/8 wave right there. And we work with half waves and 5/8 waves because we get more capture area, and we tune at the base with a tuning circuit because we want 50 ohms. A lot of this stuff is not, designed for 50 ohms, but we tune it. We'll put a tuning circuit in the base. Anyway, I'll move on. Okay, here's another one that we did. This is all over the web. This is a quarter wave at 800. But you see, it'll be offered to you at, this works from 700 to 2500. And what's going on there is that the cable is so lossy. The cable eats the SWR. The reflection coming back is so lost because the cable is so bad that the SWR meter doesn't have the reading of really what's going on at the antenna. So in antenna measurement and antenna design engineering, we always chop the cable and put the measurement equipment, the sensor, right there. So we're not measuring the cable, we're measuring the antenna. So this is like big time, all over eBay, all over the place. And I mean, I see the emails that come to you and say, 400 to, like for example, there's a lot of you guys asking for SDR. And it was the data, software-defined radio. And I sent you to the neighbor. He had packed in his SDR one of these little things. And I said, this is like minus 10 dB. You might as well just take it off and put a Q-tip on it wrap it in the foil. And he says, fine, I'll find something that's better. But antennas, especially omnidirectional, they cannot do wide frequency bands. If you ever ask for a scanner antenna, I have scanner antennas. They're not going to do 27 megahertz CB to 800. And this is how they advertise it. And it'll do it because of just getting signal from the cable. That's how crappy that is. And so again, that's not truthful. And what will help you a lot is just remembering the quarter wavelength and the half wavelength. So you're not duped into a lot of this stuff. And I think I can show you on the. Okay, here's one that was being sold by a guy in Texas. He sold a ton of them. And this is, I think it was an 850, no, this was a dual band. 850, 1900. So, they came to me and said, do something better, whatever. So we stuck this in the chamber, and we found that the radiation was horrendous up at the sky. And none of this here makes sense as a dual band. It's an impressive looking piece, so you would pay retail $30. So here, for example, is the pattern for that antenna. I don't know if this was 800 or 1900. You can see at the horizon here, where you should have like 4 or 5 dB, you're -1 and you're -4. This is the horizon right here. Okay? So that antenna is all out of tune, it's out of phase. Phase is timing. And what the coils are doing is they're timing. And you're managing either sending it up or sending it down, but with a delay, or reducing the delay between one coil and the other. So, stuff like this is dangerous because you sell these things to somebody on a boat or a car and they're depending on it to save your life because they have a flat tire or something. And these guys like this, they come over and say, would you take these off my hands? Because what happened is some cellular carrier tested them and said they were junk. And this is what they find. A 5 dB should have been, I think, out here, right around here, at the horizon. So you've got all that stuff going up at the sky. This is even worse. I think this is 800. See here, -6, -1, -11. So you could have just taken a piece of coaxial cable and radiated more than that antenna radiated. And you could tell by looking at the antenna you look at the relationship of the lengths of one section to another, especially multiband omnis. They are really hard to design. I mean, this one coming up next took like almost a year. We do this one. This thing took a year of test and error, and calculation. That whip right there, which is used for a bunch of stuff. That's on 850 and 1900. And then we've got a quarter wave here on, depends, inside we're feeding it with a capacitor. One of them acts on 1900, the other one acts on 850. So then we do a separation coil, and then we're using all this on 850, and it ignores this. That's how tricky that is. You have to do this to be ignored at 850, but it has to work at 1900. See? So that takes a long time. And in a long time, and excessive pain, just day after day. And there's a pattern, for example, of that item. And you have here 4 dB at the horizon. See? And there's the other band, probably 1900. And you have 7 dB at the horizon, right there. And it costs no more to fabricate that than the other one. It's all designed. Yeah.
Are these measurements taken as the stick is straight up and down at 0? Or
here, this here,
the stick straight
these
up?
are spurious. These are just weak spurious that are running minus, is that -3, -4, -2?
Well, I guess I'm wondering, is the measurement taken when the stick is straight up and down?
Yeah. Oh, yeah. Yes. Right. No, this is a horizon.
Okay.
So the antenna there is vertical.
Okay.
The first, image we saw was around. We just showed one because all this stuff is, it's omnidirectional within 1 dB. So what we do a lot for quick testing is just look at the horizon. What's it doing this way? That's what we're looking at. Okay, this is a ham radio 450 megahertz antenna. We don't make this or anything, but on 450, this has to be 6 inches. That actually looks a little bit long. I'm not sure. This could be on this is probably, I think that's a max red. That has to be around 6 inches right there. And then the extra, there's an 1.5 inches here extra, which was for tuning, getting SWR. But you get the relationship of size to the coil. And if it was a quarter wave, you would just have this area right here. The quarter wave is just 2 dBi. Okay? And as soon as you add all this up here, you double the power because it's double the size. So this will qualify as a 5 dBi antenna. Okay? Here's a Wi-Fi 6 or 7 dBi magnet. And again, you've got, and this is this one actually works. You've got a 5/8, a 5/8, and about a quarter, probably a half wave right here, and then the phasing coils. And that gets you the proper radiation out there. And I just don't know how to explain better, like how could you guys know when you're getting duped on this, because you can't test it. You get the cell site, it works because it's a cell site every 2 kilometers or something.
So you're just putting reliance that they have those inductors the right size at those proper frequencies. They go away.
On the other one.
Yes, the higher frequencies, you just the inductors essentially go open.
Correct.
Yeah.
The inductors only work at the given design frequency.
The lower impedance, you get the whole thing.
Yeah.
The
So
DC.
in ham radio, the guys here know that you can actually take the total length and create a totally separate antenna that ignores this. For example, if that's 12 inches long, that could be 200 and something megahertz on the 220 band.
So the low
It
frequency.
actually works.
So the low frequencies, they have to get the inductance and still have the same length of that inductor. So the whole antenna length counts the.
This will
distance.
act as an inductor, as a load.
Yeah.
That acts as a load as soon as it gets away from design frequency.
I guess I'm saying is like the length of the antenna, is that the lower frequencies, I assume it's the wire length of the entire wire that's there, or is it the length of that coil?
No.
Okay.
No. The coil acts, and the coil could be designed as a capacitor with a reactance, an RL circuit. That's what that coil is. So actually the antenna is here, then you have this matching circuit, and then the antenna is here again. And the antenna is here again.
And depending on how close those windings are, you get that capacity.
The windings are really tough to figure out. Because of the diameter of the wire, I mean, we want to go thin, but we can't because then it won't stand up. Now we're looking at log periodic antennas. This is directional antennas. This is, for example, one. Let me go. This is okay. That's what's inside. This one, for example, is if you're doing SDR, you need this and you need this. But anyway, the log periodic is a beautiful design, invented in 1957, and basically it's a wonder how it works, because it only works. You feed the frequency that you want into it, and it finds it. If you feed a very low frequency, it's going to work right around here. The middle frequency here, the lowest frequency, is going to work back here. It just finds the easiest path of least resistance. Okay? And ignores the rest of the antenna. So it's a fantastic design. In fact, all antennas are like that. They're all looking for the path of least resistance. And like electricity, like everything else. This here is just one in a housing, because this one goes from 700 here megahertz to 2700. So the elements are so thin and weak that it had to be put in a housing. Here's the electrical circuit of a log periodic. So they're fed from the front, and you can have any number of elements. The angle could be lower, like this, and the angle could be higher, like this. And you increase the gain, and you can reduce the gain. And it's a beautiful design for being an antenna. Okay, this one is one that you guys would be interested in. This is, for example, a Wi-Fi antenna. This little guy will do 2 gigahertz, 2.4, all the way to probably 6 gigahertz or 7 gigahertz. And you'll get, out of that little thing, that little printed antenna, that's loaded, that should do about 7 or 8 dBi forward. And that could be printed for nothing. It's just when the Gerber file gets a little tricky. And that takes experimentation. And that thing right there is probably about 2.5 inches long. And it's a Wi-Fi antenna, full band. It'll do 3.5 gigahertz, WiMAX, everything. Because it's continuous coverage. The center is a coaxial cable, the feed line. It's actually going all the way to the front and feeding it at the front. And that's a 50 ohm line. Normally these antennas are a 200 ohm design. But then what we do is we may be using a 75 ohm line and a matching, and maybe we played with there's an element under that you can't see that's printed, and we probably went narrow or wider to get it to 50 ohms to get SWR. Right. There's a connection at the front. Yeah, they connect at the front. Oh, here we go. This one is 2 to 11 gigahertz. And this guy here is Kent Bertain. He's a buddy of mine near Dallas. And he sells these on eBay, and I think he's retiring. But it's not him, it's him. WA5 something, I can't see it. Anyway, that thing is a beautiful design, 2 to 11 gigahertz, which we don't need.
Well, it looks like it could be a very directional thing, and it's really only using the elements that are triggered at frequency.
Right.
Because it would never be an omnidirectional.
No, because it's got on 2 gigahertz, it's going to be using just these right here, but it's got a reflector behind it and several directors in front of it, like a Yagi. So those you're making things work. This is what's the beauty of this thing. It's amazing. And remember the one you saw that was just elements in open air? that's a high gain. And because the air, there's no loading in the air between the elements. When this is all loading, all that PC board material, it's loading it. So if this was just elements in thin air, we'd be getting another 2 exponential D error. But they're so thin that we have to print them on something. See? Oh, there's another one. Okay, now we're into patch antennas. Patch antennas. A lot of the cellular and Wi-Fi on the towers is comprised of a lot of this. And if you ever open up a 2.4 gig patch antenna, I believe the rectangle, the squares, they're about 48 millimeters, which I think is like just under 2 inches. Okay? So if you see an antenna, and you don't know what frequency it's on, and you've got square the rectangle with around 47 to 49 millimeters, that's a 2.4 gig. And notice that it's half wave. It's a half wave on every side. See? So it's 2 quarter waves on every side. So that tells you, if you remember what the Wi-Fi dimensions are, a half inch on 5 gig and an inch and a quarter on the other one. That helps you figure that out. So if somebody throws an antenna on you, and you don't know what it's for, that's what I was trying to say. Here's a every patch theoretically is 8.5 dBi, and they come really close to it. They really, really do it. This stuff is really precise. Now here, you've got 8.5 plus this one, so you add another 3, and then you reduce a half dB for the losses here. So this antenna will eventually get to about 14 dBi. Okay? This antenna, you've got 3 arrays of 3 patches. So this antenna will generally get to about 18 dBi. There's 3, we've got 8 plus 3. 8 plus 3, remember, we're doubling the power because we've got 2 patches. Now a third patch gives you another 3. When you add all that up, you ended up with 18 and 19 dBi. And how they did this one was they fed 3 rows of 3. Because there's other ways of feeding it. Generally, 9 patches is not an ideal design. It's better to go 4, 8, 16. And it just gets a little bit bigger. Here's an example of one on 3.5 gigahertz that I found. And you can see they just get bigger and bigger on the arrays. These patches, by the way, are just about an inch around. This is 3.5 gig WiMAX.
And that's still very directional then?
Oh yeah, yeah. So the 8 dBi will get you 60 degrees of beamwidth. Okay, like this, and like this. Okay, everything around. Even if it's vertical polarization. When you double that to about 11 dBi, theoretically, you bring the beamwidth down by 50%, and you increase the forward power. You're doubling the forward power. So if the beamwidth was 35 degrees, you're down to 17.5 degrees, and you double the forward power. It's all mathematical. It all falls into place. See? Okay, now we're looking at a Yagi. The Yagi is made up of parasitic elements. Another totally new, another totally different design. So the Yagi is fed by a dipole here. On the side here, you can't see. And this is Mr. Yuga and Yokito Yagi did this in the 1920s. And of course, the path is all over Mr. Yagi now. And there's a driven element. That coax cable is just feeding a circuit board right there. And then this guy behind it is a little bit longer, so it rejects signal from the rear. So you got all these guys ahead of it in perfect spacing, in perfect length, working to propel that signal forward. So those are called parasitic elements. They're not connected at all to the center of the coaxial cable. This one. That's connected to the cable. Yeah, that's a dipole. It's a simple dipole. And you've seen, I've seen on the web where you can take, they have kits where you make a biquad and you put a reflector behind it. You double the power and you come up a quarter wave. Some of those things are really good. It's a dipole, and then you put a reflector, a quarter wave behind it, an inch and a quarter behind it, and now you're doing 3 dB forward. Kind of wide, but it's a start. Okay, that's it. Let me see what else notes I have here. Yeah.
Back in the early 2000s, I was working for a group that was kind of experimenting.
There's a big company now, fractalantennas.com or something. There's people that believe in this. I'm going. It's just for wide banding. There's something called ultra wideband, UWB, and you need it for that. Yeah. Let me see what else I didn't cover here. Gain antennas, I release the size. So all I was trying to say was you need to know something about a relationship of the size of an antenna to the gain of the antenna and the performance and the frequency. Sometimes you find an antenna at a flea market and you're afraid to buy it because you don't know where it is. And if you just analyze it a little bit, take a picture, take it home, email it to me, whatever, I can usually tell. Just with 2 seconds, I can actually estimate the gain. I've been at this for 40 years maybe. I can estimate the gain. I can tell if it's badly designed or not, kind of, I can get a feel for it. You had a question?
Yeah, I was going to ask, is there any pattern in particular that's the most directional? Like log periodic or Yagis?
The log periodics, they're limited. Because you noticed there's only 2 or 3 elements working at a time. So a log, we never get narrower and more powerful than about 12 dBi. The best log periodic, the one in that plastic housing, that thing was like 12 dBi. That's like, that's cutting edge on that. But most of them, like those printed ones, they're only doing about 7, 6, 7, 8. So then it's wide, and it's like 50 degrees wide. And to be honest, the beauty of the log is the wide band, because I can just do a patch in 15 minutes to do the same gain as that log did. But I would have to do a patch every 200 megahertz, a new patch antenna, the little squares. Yeah. So the beauty of the log periodic is that it does everything for you. The only problem with log periodics is if you connect them to a cheap radio, you put up a log in a city, and he's an open ear for everything in that frequency. So you have to have a really good radio that can reject all that stuff.
So if a log will do 12 dBi, best case, what would a Yagi do? Best case?
The Yagi best case, because there's a law of diminishing return, and that's a good point. You see Yagis on eBay, for example, that are saying 20 dBi. And for 2.4 gig Yagi at 20 dBi, I think it has to be about 6 or 7 feet long. But they're giving you something that's about 3 feet long. So that's a no-brainer. When you see stuff like that, and the other one that's all over the eBay is the Wi-Fi Yagi with a fat center aluminum square tube and very short elements. And they're calling it maybe 16 dBi. Those things are doing like 9 or 10 because it's extremely inefficient. That's why we use patches and a lot of patches at higher frequencies. Yeah. I think one down and one up would be good. Those, if you have like on your home router, you have a little 4-inch stick. Those radiation patterns are mostly round, and very few of them. If you get into a taller stick like this, then you have this flat pattern, then you've got to be very vertical. But because in your house the signals are bouncing around a bit, and the radiation from those things, I was gonna get a water balloon or an air balloon and just show you how. These examples are all over the web. You can see, you can take a balloon and just start squeezing it down, and you start bringing the signal out where you want it. You see? So antennas are signal managing. But I would try, if it's a really short one over and one up. But if they're like 6 inches, they've got some gain to them, so there's more here, then you just have them like this. And any other interesting... Yeah, I have an Anechoic chamber we set up in 2003 in Miami. It's 28 feet by 14 by 14. And I actually went to Georgia Tech for an intensive week before I spent all that money, and so I had to educate myself on what to buy. And it's got a lot of these. There's a website called antennatesting.com. I wish I would have had some pictures, but then we get too complicated. And it's just covered in cones that are impregnated with lead. Well, I mean, I'll say lead. That's very bad for you. I think it's graphite or something. And then it's got salt for fire protection and all that. And then this is a huge metal box, and it's 28 by 14 by 14, double layer metal to reject the signals that are around us. And in there, we have, for example, a 40 dB isolation between what's outside and what's inside, and 40 dBs against. It's called anechoic, for example. So we have 40 dB down of any reflection coming back, because I'm in a metal box. So I'm shooting a signal from here, and then we're rotating an antenna on the other side and rotating it like this. So we're doing this, and we're generating a 3-dimensional pattern. And I think you saw some of those patterns there. That was a quick shot. What you saw there, the elevation, that's just one slice. It's just taking a slice. But when we have a bigger project or a customer that says we need it all, that chamber, it's automated. The computer runs it, the rotors, everything's automated, so we can walk away. And it'll just spend 2 hours taking a slice every 1 degree. I mean, just over and over again. And then that creates these beautiful balloons of wire mesh, and then we can put colors in it and everything. And my favorite days are the days that I can spend playing with my toys in the chamber. And the trouble is you got to run the business too. But we did a lot of development work for XM and Sirius, XM before the Sirius bought them. And then who else? Motorola. So I had a lot of people there developing antennas. I saw a lot of the really neat stuff that XM was doing. And then when Sirius bought them, they moved everything to New Jersey. They still have an R&D facility in Boca, about 60 miles north of Miami. So we still interact with them. And some of the guys there mentored me on some of the tiny antennas. And because I was more into bigger, more basic antennas for 800 megahertz. And I had to learn how to do satellite antennas. And as you may know, satellite antennas are sending a circular signal, like this. So when the satellite is changing position, it doesn't matter to the antenna, to the receiving station. Because if you have, and I should mention that, if you have vertical polarization on your antenna, like he asked about the vertical, and then you flip it over. So for example, you have a grid up there, and the grid is, the parabolic is this way, and you see that feed horn? The tip of the parabolic is called the feed horn. When you turn it over, you can reject your neighbors and the crowd around you by 3 to 7 or 8 dB. Depends on the antenna. Remember, 3 dB is half. Another 3 dB is another half. So if you turn this, you're running from your office to your home, a Wi-Fi network. If you turn it sideways, you could be cutting down the interference by about 75%. Now, the only drawback is that the reason why everything's vertical, police cars, mobiles, everything, especially vehicles, is that the horizontal signal gets more ground effect. The horizontal signal can bounce off the ground and come back up. The vertical signal is, it's just blade, okay? And in doing data, when you have any bouncing, now you have a delay. You've got a direct signal and a delay signal, and it screws up your packets, it screws up your data, especially with what we're doing these days, everything data. In the analog days, you get some You know, like on the TV ghosting, that's phase. You remember the old TV? You would get a ghost. That's phase. One side of your antenna was getting the signal before the other. When you were not aligned, that's called phase. And phase is timing. And that nanosecond created that ghost. So, and what happens is everything is vertical pole. The ham radio, they use HF, and as soon as it bounces off the ionosphere and the ground, it goes horizontal. It cannot bounce
They always
vertical.
have TVs back in the day where the antennas always went 45 degrees typically.
Because it got too wide. No, the TV, they transmit horizontal, by the way.
Also, it should have been this way.
Yeah. Your TVs are that way.
One of the ones you mentioned, decent antenna designs that were clobbered by crappy cable.
Yeah, I mean, you guys have to deal with this all the time. You see advertised coaxial cable, and you see the fat coaxial cable, and you see LMR coaxial cable. For example, on Wi-Fi, I won't run more than 10 feet of an of a cord. It's 3/16, like RG58 diameter. RG is LMR 195, which is a double shield. I will not sell or make more than 10 feet of that at 2.4 gigabits. I don't know the loss factor by heart, but there's attenuation calculator on Google that you can look up. And then after that, you have quarter-inch cable, which is LMR 240. And that 240 counts because it's 0.240 inch. LMR 195 is 0.195 inch, which is 3/16. And then LMR 400, which is a fat cable. For ham radio, you have RGA. But, we're using double shield, and it's the same diameter. It's 0.4 inch, so it's called LMR 400. That stuff, even running 50 feet of that, at the Wi-Fi, the lower Wi-Fi, you're losing 35-40% of the signal. So that's why we're trying to get away from that and just put a radio up there, an access point up, just run the cheap Cat5. And a lot of people now in the industry, they're having us make the antenna to use TV cable, RG6. This is 75 ohm cable, so that means we're raising the SWR. But in practical sense, these guys are not that far out. Because you go from an LMR 240, which costs at retail 45 cents a foot, to an RG6, which is your TV antenna cable. That stuff is 10 cents a foot. Okay? And what are you losing? 5%. So it's really getting confusing now, because now we're using F connectors, which are 75 ohm connectors, on 50 ohm cable, and vice versa. So, but it's a huge cost savings. And the reason the RG6 and TV antenna cable is so cheap is because they're pumping out in China like 1 billion feet a day. So that's what's making it so cheap. And they know it's for TV, and it doesn't have to be such high quality. You got a question? Which one? Chip antennas, I did that many years ago. Anyway, a chip antenna is just a way to spit out some kind of a signal. And these are, if you look on your circuit boards or a cell phone, for example, a lot of cell phones now, they'll have like a tiny strip of metal, or in your laptop, at the upper screen, there'll be a multiband antenna. And the chip, what the chip is doing is it's a substrate, which is I don't know what the hell is it. I can't remember what it's made out of. And they go thick. And what they're doing is they're loading. So, for example, you take a dipole antenna, that quarter wave, which is 1 1/4 inch, and you encase it in a loading material, like plastic, or some sorts of plastic, some sorts of rubber. So that 1 1/4 inch now becomes much smaller. You still get resonance, SWR, but now it became tiny. You can go down, you can load the hell out of it and make it 1/10 of an inch antenna. And what you're losing is efficiency. Instead of doing 2 dBi, now it's just this little globe of -4, And that's what the chip antennas are doing. They're doing -4, -6, -7. And the reason they work is because they've got a really good receiver on there, so they're spending the money on making a fantastic receiver, and then the cell site or the Wi-Fi AP or whatever is coming in is pumping a lot of power. And that's how they work. And what's a substrate called? Oh, you know what's a perfect example of a big on-chip antenna? Your GPS antennas. If you're looking at GPS antenna, you'll see a printed, maybe a little square, like a 1/2-inch square. This is 1.5 gigahertz. And that's on top of like a sandy-looking white square, which is maybe 2 or 3 millimeters thick. That's the loading. That thing there is probably doing -2 dBi, right? If you start getting rid of that loading, that tiny 1/2-inch patch becomes, it could become 1.5 inches square, and now you're getting 6 dBi, 7 dBi, see? But you're still resonating.
You mean FR4, right? The material substrate?
No, actually, it's like a sandy ceramic. Ceramic is what they're using. Yeah, yeah.
So, like, Google and a couple companies are experimenting with using white space and TV signals.
Yeah.
Have you heard about this?
Yeah.
Like, what's going to be the level?
802.11.22 maybe or something like that.
Yeah, like, what are your thoughts on? Do you think it's like a practical option?
It's very low power, and in fact, on our website, we put up a TV log periodic, like the one up there, and we put all the keywords: white space, 802.11, or 802.16, CC, whatever it's called, and it's in the beginning. And I think it has a possible good future because it's a low frequency, so you get penetration to the walls compared to what we're doing up. That's why 4G, AT&T, 4G, AT&T, and Verizon, they went to 700. They went down to get penetration through the walls and through the trees better. Anything that resonates will eat your signal. Okay, for example, if you had a wall loaded with 1 1/4-inch screws, you're not going to get a signal through on Wi-Fi. In Florida, in Miami, there was a street out on 40, it's called US 41, loaded with pine trees. The pine needles were like, I think like 3-inch pine needles. And guess what? That was a quarter wave on 850. So the cell signal was crap. It was like hitting a brick wall. And eventually they took them down because development took over. But they resonated perfectly.
Tree huggers like that, I bet.
Yeah. So, you know, and that's how they can attend. This is the same theory behind the Yagi. You do a certain amount of size behind the Yagi, and you're blocking everything behind it in the right spacing.
So when you say weak, like how weak are the signals? Like, or like what kind of speed would that translate into on like Wi-Fi?
I mean, in dBi or dB, I mean the signals are. You mean the white space?
Yeah. So like
it's very weak because they're allowing maybe 1 or 2 watts out, and they've got all kinds of limitations. It's starting off already being shot in the foot. Yeah. So we'll see where it goes. Okay. Time to go.
Thanks a lot.
You're welcome.
May send you an email in a couple days.
Great.
I have a few things I'm looking at.